Hi everyone. We're going to take what feels like a little bit of a tangent, a little bit of a sidetrack, but it does tie into inequalities, and it is something kind of a notation piece that we'll need to understand. So we're going to look at compound inequalities. We've actually already looked at one. We've looked at things like 2 is less than x is less than 7, the between statements. Those are compound inequalities. That's an and statement, really. That just has a nice abbreviated way to write it. So we're going to look at two versions of this notation. We're going to look at the inequality version, which is going to be the and or the or, and then we're going to look at the interval version, which is the intersection or the union. So and statements, otherwise known as intersection, can be used to hook two inequalities together. So we can have one inequality, we can put and in the middle, write another inequality. And that whole statement will only be true if both inequalities are true. So that is called intersection. And for a nice visual, I really like the Venn diagram version of this. If this is set A and this is set B, the values that make A and B true are in here. This is the A intersect B, or A and B. So the intersection of two sets is the and. Or is the other one, and this is basically just the combination of the two sets. I see a T in union there. So union of two sets, that's true whenever we find a value that's in A or B or both. So the entire combination of the two sets would be the union, and that would be or. So what we want to do is look at our inequalities, and I think a number line of a graphical look at those things is one of the easiest ways to pick out where's the intersection, where's the union. And one thing that we're going to be trying to do is see if we can write them in a little bit simpler fashion. So they're all, I guess there's some betweens, but mostly they're going to start out as an and or an or, and sometimes you can write that in a shorter way. You only need one statement once you look at what numbers you're actually getting. So first one, the work in solving compound inequalities and finding the solution sets, or the values that make the or statement or and statement true, will be to look at the graphs of the two individually. So my work, and I'm labeling this really carefully because sometimes people get confused and they think that drawing the two individually is their answer. It's not, it's just your work. So I'm going to say, okay, we have x less than 2, which looks like this. So all of those numbers make the first statement true. And then we have x less than or equal to negative 1/2. Let's see if I can snag another color out of this. Red. Negative 1/2 is in here. And that gets a closed circle. That goes this way. Okay, so this is just my work. My answer is going to come from looking at what's connecting the two, which is an or statement, and saying, okay, so or is true if either one of the statements is true or if both are true. So over here, statement 1 and statement 2 both true, which means the or statement is true, and that continues all the way up to negative 1/2, both are true. After that, I'm still hitting the first inequality solutions, so I'm still satisfying the or statement. One or both are true, and that continues until I get to 2. Once I get to 2 and then anywhere to the right of 2, neither one of those statements is true, which means the or statement isn't true. So I'm looking for the combination of the two sets, and I can summarize that. So this is my answer by saying, okay, anything from 2 over works for the or statement. So in this case, there's no reason to write the or statement. You can just summarize this as x is less than 2 gives you all the truth values, all the solutions for the or statement, the compound inequality, or we can say negative infinity to 2, not including 2. So you're looking for any where that one or both of the statements are true. For an and statement, color things in the way. Okay. So this again is my work. We don't want to be confused. You have to try and simplify. Sometimes they don't simplify, but I think most of these will. So let's see here. The first one says x is greater than 3.2. 1, 2, 3. Okay, so here's 3.2, pretend, and it gets an open circle, and we want everything bigger than 3.2. And then for the other one, we want everything greater than or equal to 0.7. So 0.7 is right around here, and we want a closed circle. Okay, so again, going the same direction, but this time when we go to figure out our solutions, we're working on an and statement. So in order to make the and statement true, both of the inequalities have to be satisfied. So if I start over here, neither one is true. When I get to 0.7 and all the way up through 3.2, one of the statements is true. That's not good enough for and. And is the intersection. So we're looking for where the two statements overlap, which is going to be anywhere past 3.2. The two inequalities overlap if x is greater than 3.2. So this is my answer. This is the graph of my answer. And that means that we don't really need the greater than or equal to 0.7 at all in order to make those both true. We just have to make sure that x is greater than 3.2, or we can say anything from 3.2 to infinity. And that's going to be our solution. Okay, so and is overlap, or is both of the two smushed together. Or seems a little harder to word, but hopefully it won't give you too much trouble. Okay, x greater than 1.5 or x less than 5. So these are going opposite directions. So go blue, greater than 1.5, less than 5. Okay, so let's say we'll put 0, 1, 2, 3, 4, 5. Okay, so 1.5 needs an open circle, and we want everything bigger than 1.5, so headed this direction. Less than 0.5, who's choosing? Oh, this is good. We need an open circle at 5, and we want everything smaller than that. So so this is my work. Look at the two separately. My answer is to then summarize any x values that make both statements true. So where do the statements overlap? And the answer is everywhere from 1.5 to 5, but not including 1.5 or 5. There is, oh wait a minute, I'm sorry. Confusing my own self. We're not looking for and, we're looking for or. So or statement is wherever either one or both is true. So if we start from the left all the way to negative infinity, we're in good shape because x less than 5 will be true. And that actually continues. X less than 5 is true all the way up to here, 5. And after that, we're actually still good forever because x greater than 1.5 is going to be true all the way to positive infinity. So for the or statement, we actually get all real numbers. There isn't anything that doesn't satisfy one of those two. So here we'll just put 0 in the middle. So for inequality notation, I would just say all real numbers. For interval notation, negative infinity to infinity. So when they're pointing opposite directions, nice things can happen. They don't always overlap, and that's a different story, but that one's kind of nice. We get all real numbers. Okay, So this is the implied and statement. So here we're saying that, and these are actually, I hope, easy because they, if you remember, they just directly translate to between. So if you're understanding that that's what that notation means, makes it easy to jump straight to what it looks like without having to even draw the two separate inequalities. So x is between negative 2/3 and 1/4. So here's negative 2/3, and here's 1/4. And we don't want to include either one, but we want everything in between. So this is actually an implied and statement. This is the same thing as saying x is greater than negative 2/3 and x is less than 1/4. And since it's an and, we would only take the overlap. But again, when it's written that way, that's kind of a hopefully like a cheat for you, because if you remember that that means between, when you write x between them, it means between, then you don't even have to do the overlap part. Okay, couple more, so you can see hopefully some of the weird things that happen. X is greater than 4 and x is less than negative 1/8. Okay, so 0, 1, 2, 3, 4. Greater than or equal to 4. Oh, I guess I could choose some colors. And then less than, so let's say negative 1/8 is right around there. Negative 1/8. Okay, so this is going opposite directions and they don't overlap. So if this were an or statement, there would be no way to simplify it. There's no simpler way to say that you have these two totally separate pieces that don't overlap. Because it's an and statement, we're actually in trouble because and is asking when do they overlap, and these never overlap. So there is no way to make this and statement true. This is actually a contradiction. So my answer is nothing. These are x values, which means you could say no solution would be great. An abbreviation for that would be empty set. There isn't anything in the solution set. Inequality. I don't know if there's a nice inequality. I can't think of any way to write an inequality that represents this. So no solutions to that one. There's no way to make that and statement true. Okay, I want to play around a little bit with the does not equal. These are interesting. This comes up when we're working on complicated problems where we're talking about what we can and can't plug into an equation. So this is kind of an interesting one. So we are trying to combine the statements. X is greater than 3.5. So let's say this is 0, 2, 4, 6, 8. Okay, so greater than 3.5, hold on. That would be about 3. So let's say that is 3.5. And we want everything from there over. And then x does not equal 7. Remember, that means x can be anything but 7. So if this is 7 right in the middle here, we give that an open circle and we take everything to the right and we take everything to the left. And we're looking for the overlap only, so they both have to be true, which means we'll get everything from 3.5 over, excluding 7. So as far as inequality notation is concerned, there's not a better way to say that. I can do a better job of drawing that. So starting at 3.5 and leaving one value out at 7. Otherwise including everything to the right. So that's what it looks like, but there's not really a better way to write that with inequality notation. You could write it as 3.5 less than x less than 7, or x greater than 7. That's just a different way. I don't think it's better. In fact, it looks a little longer to me, so kind of a wash on that one. If I can remember which one, interval, there we go, I keep wanting to say inequality, interval notation, that one we have to kind of follow the format we just used. We would say we start at 3.5 without including it, we stop at 7, we start back up at 7 and we go to infinity, and we want the union of those two, not where they overlap. Those don't overlap. We want the combination of both. So there are definitely statements that don't really simplify, and that would be a good example. Okay, one more, same idea, but with an or, kind of the same idea. Okay, so x, okay, so we want, let's put 0 here. So here's negative 1, 1, 2, 3. Okay, so we are looking at, where the heck did my color thing go? Oh, all the way down at the bottom. Okay, well, no colors because I lost the little thing. So x less than negative 1 looks like this. X not equal to 3 includes everything but 3. So again, this is just my kind of like my scratch work, right? So I'm looking at the 2, and it's an or statement. The or statement is going to be true as long as one or both are true. So they're both true over here. That's great. I should kind of hesitate at negative 1 because the bottom one isn't true, but the or statement doesn't care. The or statement is totally happy with just 1 being true, so we're still good. And we continue to be good until we get to 3. 3 we really do have a problem because neither one is true at 3. But then as soon as we move to the right of 3, we're good all the way to positive infinity because the not equal to statement is true. So we can actually simplify this. Really, the x less than or equal to, or sorry, the x less than negative 1 doesn't tell us anything that we don't already know just by saying 0, 1, 2, 3. X can be anything but 3. So the first part of that statement doesn't actually add any information. They're both true as long as x is not equal to 3. Okay, so they get a little funny. So we're going to try not to get too crazy with these, but I do just want you to be a little bit familiar with connecting statements like this. All right, thanks for watching.